Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 30th, 2025, exactly 1 week ago. It identifies a critical flaw in how researchers evaluate data recipes, and shows that simply using tiny learning rates can boost the ranking correlation between small proxy models and large target models from under 0.75 to over 0.95. The paper is titled, "Can Small Training Runs Reliably Guide Data Curation? Rethinking Proxy Model Practice." And as we'll see later, the results suggest a practical way to stop wasting compute on misleading experiments. To visualize this impact, Figure 2 compares the rankings of 23 data recipes between a small proxy model and a larger target model. The left panel shows the results using a standard learning rate, and notice how the connecting lines are chaotic and crossed, indicating that the proxy is giving misleading advice. In contrast, the right panel uses the proposed tiny learning rate. Here, the rankings align almost perfectly, meaning the small model can finally be trusted to guide the large-scale training. Well, Figure 1 steps back to illustrate the standard industrial workflow. On the left, during the data preparation phase, teams evaluate candidate datasets, labeled D1 through D3, using small proxy models with fixed, identical hyperparameters. Once a winner is picked, the process moves to the right panel, where the model training phase begins. Here, that chosen dataset undergoes extensive hyperparameter tuning for the large target model, which creates a fundamental mismatch between the rigid proxy search and the flexible final deployment. Well, Figure 4 provides the empirical proof that this tiny learning rate strategy acts as a reliable shortcut. Panel A on the left plots the validation loss from a cheap run using a tiny learning rate against the best possible loss found through expensive hyperparameter tuning. The points line up tightly with a Spearman correlation of 0.97, which means the simple proxy effectively predicts a dataset's peak potential without the tuning cost. Panel B on the right confirms this holds when scaling up the model size. The dark red block in the bottom left corner shows that high-ranking consistency between small and large models only exists when both use these reduced learning rates. So, Figure 6 confirms this stability across multiple model families. Panel A on the left plots ranking correlation against the proxy's learning rate, showing that as the rate drops towards the left, the consistency with the target model spikes above 0.9 for GPT-2, Pythia, and OPT. Next, panels B and C illustrate the decision regret, or the performance gap between the proxy's choice and the true best dataset. In both validation loss and benchmark accuracy, the pink curves for the tiny learning rate approach stay much lower than the standard blue baselines, indicating that this method reliably finds the optimal data recipes. Alright, while the previous figure focused on global averages, Figure 5 breaks down the rank correlation by individual domains and benchmarks. The orange bars, representing the tiny learning rate proxy, consistently reach high correlations across the board. In contrast, the blue bars for the standard learning rate are unstable, often dropping into negative territory. You can see this clearly on the left with domains like GitHub and ArcSvive, where the standard proxy fails to provide any useful signal. This gap persists on the right for benchmarks like HelloSwag, proving that the tiny learning rate is superior across diverse data distributions. So, having seen the performance gains, Table 1 details the 23 dataset recipes used to validate them. The first category is domain composition, where the researchers vary the mix of sources like Stack Exchange and ArcSvive to see how content balance affects learning. Next, they test established datasets including C4 and Refined Web. The bottom half covers quality filters using Red Pajama v2 partitions, and finally, deduplication strength, ensuring the method holds up across the most common data curation levers. Wrapping up, 2 takeaways stand out. Standard proxy evaluations are inherently brittle because they ignore how data interacts with hyperparameters. Yet, by simply lowering the learning rate, teams can ensure their small-scale experiments accurately predict full-scale performance, saving massive compute resources. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.